Now we know how research is designed and how evidence is collected, it's time to figure out what we do with all that data. And there's two main categories of data analysis: descriptive statistics and inferential statistics. Descriptive statistics are used to summarize and organize data. They describe, but don't go further than that. These stats answer questions like, what's the average hemoglobin level in this population? Or how many participants met the protein recommendation? Descriptive statistics are the what in the data. They help us identify patterns and describe characteristics like mean, median, mode, and standard deviation. And we'll go through those metrics in more detail in just a minute. Inferential statistics go further. They let us make educated guesses about a larger group based on data from a sample. These statistics help answer questions like, did the intervention actually make a difference, or was this result just due to chance? Inferential statistics are the basis for things like p-value and confidence intervals, which we'll cover in the next video. But the takeaway here is that descriptive statistics describe. Inferential statistics help us interpret and apply. Both are important, and as we move forward, we'll learn how to better understand what data is really telling us. But before we start calculating averages, we need to understand one very important concept. Not all data is evenly spread. That's called skewness. A normal distribution is perfectly symmetrical. Like a classic bell-shaped curve, most values cluster around the center, and fewer values appear as you move out to the ends. Many biological measurements follow a roughly normal distribution, like height or fasting blood glucose in a healthy population. But not all data is normal. Sometimes the values stretch out more on one side, and that's called skew. If the tail is on the left, we say that the data is left skewed or negatively skewed. This means the bulk of the values are higher, but there are a few very low values pulling the average down. An example might be fiber intake in dietitians. Most dietitians eat a moderate to high fiber diet, but there are a few dietitians who don't take in high levels of fiber, which skews the data to the left or negatively. On the other hand, if it tails to the right, we call it a right skew or a positive skew. In this case, most values are low to moderate, but there are a few unusually high values that pull the average up. Sodium intake in the general population is a good example. Most people fall in a typical range, but some individuals consume very high levels, which shifts the distribution to the right. The important thing here to understand is that skew affects how we can interpret the data. It distorts the mean and makes it less reliable as a measure of central tendency, and that's why sometimes we prefer to use median. Let's take a closer look at those measurements. When we want to describe where the center of a data set is, we turn to three key measurements: the mean, the median, and the mode. The mean is what most people think of as the average. You add up all the values and divide by how many there are. It's a great summary, but it can be easily influenced by outliers or skew. One extremely high or low value can pull the mean up or down. And so the median is the midpoint of the data set. You arrange all the values in order and find the one that falls exactly in the middle. And if there's an even number of values, you take the average of the two central numbers. The median is especially helpful when data is skewed because it isn't affected by extreme values. The mode is simply the number that appears most often. It's not used as often in nutrition studies, but it can still be useful, especially when describing categorical or ordinal data. In perfectly symmetrical normal distribution, the mean, median, and mode are all the same. But when the data is skewed, they start to separate. In those cases, median is often used as it's the most accurate reflection of the center. Keep that in mind as we work through some examples. Let's try this out with a real data set. In this data set, we have the values 12, 15, 12, 18, 20, 15, and 25. Let's work through it together. So the mean is the average, and to find the average, we're going to add up all these numbers and divide by the total that we have. We have 7 numbers in our data set here. So if we add up all those numbers and divide by 7, we'll get our mean, which is 16.7. The median is the middle value. Now to figure out the middle value, I like to put my numbers in order. So if we put the numbers in order, they would go 12, 12, 15, 15, 18, 20, and 25. And then cross off your low number and your high number. Cross off your second low number and your second high number. Cross off your third low number and your third high number, and you're left with the median. And if there was an even number of data points here, like for instance, if 15 and 16 were both left over, you would average those two together to get 15.5. But that's not what we have here. So the mode is the number that appears most often. In this case, both 12 and 15 show up twice, which means this data set has two modes. And each of these values tells us something different about the data set. Now let's shift from numbers to visuals, because sometimes it's easier to see what's going on in your data when you graph it. Histograms are one of the most common tools. They show how data is distributed across intervals or categories. On the x-axis, you have the values grouped into ranges, and on the y-axis, you have frequency, or how often those values occur. A histogram is technically a type of frequency distribution. Frequency distributions just refer to any method of organizing data by how often the values occur. They can be displayed in tables or graphs, including histograms, bar charts, or line plots. These visual tools help you spot patterns that may not be obvious in raw numbers. You can see whether the data is symmetrical or normal, whether it's skewed, and whether there are any gaps, any clusters, or outliers, which is incredibly helpful in nutrition when trying to understand things like nutrient intake across a population. And when you graph large data sets, patterns begin to emerge. One of the most important reasons we use histograms and frequency distributions is to see their patterns. They help us see the shape of the data. For instance, we can see the median, which is the center part of the data, and you should also notice the axes. On the x-axis, we place the independent variable, the one we are studying. This could be something like age group, diet type, or intervention phase. If time is an option, it's the independent variable. On the y-axis, we plot the dependent variable, the one that responds to changes in the independent variable. That might look something like cholesterol level, weight loss, or calcium intake. In both frequency distributions and histograms, on the y-axis, we plot the frequency, or how often our independent variable is happening. Knowing what goes on each axis is critical when interpreting research graphs, and it is necessary to understand relationships between variables. Range is one of the simplest ways we can describe variability in the data set, because it tells us how spread out the values are by showing the difference between the maximum value and the minimum value in a data set. To calculate the range, you just subtract the smallest number from the largest. So in this data set right here, 12, 15, 12, 18, 20, 15, and 25, the range is the difference between the biggest number, 25, and the smallest number, 12. So the range in this case would be 13. This means there's a 13-unit spread between the lowest and highest values. The range is a quick way to measure variability, but it only gives you the outer limits. It doesn't tell you anything about what happens in between. If all the values are tightly packed within those boundaries or widely scattered, the range doesn't reflect that. For that kind of detail, we need to look at the standard deviation. And I definitely expect a question on standard deviation on the RD exam because standard deviation is one of the most important tools in statistics. It tells us how much the data varies from the center. If the standard deviation is small, then the data points are clustered closely around the average. If the standard deviation is large, then the data is going to be more spread out. Much of nutrition data can be analyzed using standard deviation because most nutrition data is represented by a normal distribution. Think about average protein intake or serum sodium levels, even BMI. Some people are above, some people are below, and most people fall right in the middle. This kind of data is called a normal distribution, also known as a bell curve because of their shape. So standard deviation gives us a way to predict how much of the data falls within a certain range. From the center, one standard deviation in either direction covers about 68% of the data. 2 standard deviations cover 95%, and 3 standard deviations are 99% of all of the values. So to think through this, let's imagine a study that's looking at BMI values in a large group of adults. If the center or average BMI is 24 and the standard deviation is 2, then 68% of the group has a BMI between 22 and 26. 68% of the group is 1 standard deviation. So to figure out the range of 1 standard deviation, we take the middle point and then we add and subtract 2 on either side because our standard deviation is 2. Almost everybody, 95% of people, fall between 20 and 28, which is 2 standard deviations. Again, since the standard deviation is 2, Then 2 standard deviations is plus or minus 4 from the middle points. And then practically everyone in the study, 99.7% of the people that are represented in this population set, have a BMI within 3 standard deviations, or between 18 and 30. Standard deviation helps us understand what's normal, what's high, and what's low. And in clinical nutrition, it guides decision making when interpreting lab values and patient outcomes. So when you see standard deviation in a study, it's telling you how reliable that average really is. It's giving you context for how the data behaves.